Okay, thank you for joining our data decision loop talk. Before we start, I'd like to remind you we're available for chat, and you can click the chat button on the bottom right there and submit any questions. We'd like to thank Carl and the team at LunarG and Benoit, the team at Imaginary Spaces. There's a lot of very intense, cutting-edge research R&D we're showing today, and they've been a great partner for all that, and we're very grateful for their collaboration. Okay, so big picture, the data decision loop. When you think deeply about data, and if you have friends working in the area and you get in a deep conversation about it, you often end up thinking about this iteration loop of the worker and how you're carving through these giant piles of data and you're making discoveries, and those are leading to new discoveries, new questions, new interactions, and it sort of comes down to this fundamental core of data. And so with that as a backdrop, we've had this question for a long time. Could data work be better if you put as much as possible on the GPU? The GPU is a frontier of performance and kind of cutting edge computing right now, parallelization. And the question is also, what areas of data work could the GPU address? Programming on the GPU is difficult, it's time consuming, it's a kind of tough area, but it's a frontier. And so there's more available, what's available. And if we look over history, and these are some kind of highlights we've chosen in data science history, the spreadsheet. But as a kind of overall picture, they have this trend of reducing the cognitive load, lowering this decision loop, and bringing decisions and thoughts and reducing the cognitive load. So I would say Spreadsheet is a great example of that. Python is an example that simplified data coding and swept the industry. Pandas kind of brought the thinking of the spreadsheet to code. And then AlexNet is also this great breakthrough where it took a computation task that took weeks and collapsed them into a much smaller time scale. And so you can see across the history of data science, there is this kind of breakthrough. It's not always about a better algorithm or better math. The worker, the time to make decisions and carve through iteration is incredibly important. And so when you think of people doing data work, there's some different ways of thinking about it. We've segmented the market into two parts. So there's sort of the expert zone, the expert market, which you could call the machine learning market, and then there's the business and consumer market. So that scales to billion, up to 1 billion users, everyone in their cupcake shop doing their accounting. So in the machine learning market, we're looking at what are people doing? What is the work involved? And this was an interesting survey. You can see the majority of expert data work in machine learning revolves around the IDE. And that's sort of an interesting area. Surprisingly, the spreadsheet ranked as number 2 in this Kaggle survey. And then from there, you go down to the traditional business intelligence software, cloud, stats, things like that. In the business and consumer market, again, this is less surprising. The spreadsheet shoots to the top as the everyday tool where you can just sort of sketch out data problems. But the development IDE is also significantly more used than anything else. So when we're looking at these areas, these segments of data work, you can think of them like it's hard to implement things on the GPU, and most computing is done on the CPU, just one core or multi-threading right now. So if we look at this difficulty of doing things and their impact, we can see, well, there's this kind of, there's the low-hanging fruit of display and UI, which is primarily the video game industry. And there's machine learning and AI, which is very difficult to implement, but is so valuable. There's an enormous focal point on that. So today we're going to look at this whole area. And what we're going to say is, where are we? Where's the frontier? What is the potential impact? This is an area our team and our partners, we spent a ton of time looking at how these things can be accelerated. So we're going to share some of that, some of the things we've learned, and ask the question, could these things be unified in terms of the decision loop, how could these things be collapsed into this sort of lightning speed quick loop? Okay, so looking at display and UI, this is dominated by the game industry, and they're very innovative. Surprisingly, the data industry tends to avoid GPU display. Instead, they tend to favor JavaScript, Qt, Windows UI, these kind of things. So this is a low-hanging fruit for big impact. And in parallel with the GPU performance is this idea of this immediate mode revolution. So immediate mode UI is similar to game programming. You're submitting triangles and you're only looking at, it's sort of a view-dependent way of doing UI. And this is a quote I think a lot of UI people about interested in UI performance love, from Michael Abrash: the fastest instruction is the one that is never executed. And this sort of mindset of performance brings you to the GPU. And, you know, people tend to, the human mind kind of likes to divide things into camps and sports teams. You'd think, oh, the desktop and the cloud, often in data, they're seen as different approaches. But if you look at gaming, I think they're incredibly innovative of taking the power of the local machine, the local GPU, and then integrating server as well. And so this idea of the desktop as a frontier of low latency, the GPU, as of last year with the Ampere architecture, has incredible power. And so when you look, you compare the power of low latency and the time for like a mem copy from the CPU to the GPU, and then you compare that with moving stuff around a data center, around network clustering, about web calls. These things are getting faster, but they don't compare to these lightning speeds of being local, being desktop driven. So if we look at that in software, there's some of our tests that we've been doing. Recording, you can see if you're at 10 million records, well, we'll just start off with 900K records, that, you know, we know this, the CPU is slower. The GPU can just have a lightning speed to grab data off an SSD and get it up on the screen. And you see, we're going to get to larger scales in a minute, but you can see as the scale increases, the CPU just basically is not up for the task. For example, Excel has difficulty loading over 1 million records and displaying them. So if you look at this thing gone right, so this is looking in the guts of execution. It's not just the GPU, it's the orchestration of cutting edge parts. So if you look here, we've got 16 cores, and this is showing a submit to the GPU inside our software. It's got all cores chugging away, cranking to get this piece of data onto the GPU, like a chainsaw carving through them in one shot, throws it up to the GPU, and then comes down. Every core goes crazy, feeding that data back to the display. And so this is kind of the best case. It's this incredible orchestration problem it's an incredible frontier as well. And if you take network clustering as one point of view, and then you say, okay, well, the other side is we're just going to do everything with the CPU, GPU, SSD interaction. What happens is you collapse space, you collapse time. You're in a low latency area. And so you can start to profile these just looking at the functions and looking at these GPU tuning mechanisms. And so if we look at another area, data search, basically there's just a mind-blowing sea change happening right now. Network clustering, this is something that went unnoticed in 2020. At the end of 2020, the Ampere architecture was released by NVIDIA. And this is a groundbreaking step forward in desktop overtaking the scales of network clustering. And so NVIDIA Rapids team has been doing trailblazing work here for a long time. But in this example, we're looking at sorting a billion records. And you can see this is the Turing architecture. It is significantly slower. The Ampere architecture has made a big gain forward to do a billion records. And if you look at the 1660, they can't reach that scale. So you can see this is a GPU is just moving fast. In fact, internally, we got this number here down to 46 seconds. But the day before the presentation, so we couldn't show it. Okay, now let's look at this in terms of growth. So here we're sorting 0 records. We're doing compute on the GPU, and you can see it's just a very efficient orchestration mechanism. So we've got, it's interesting to watch the 3090 and the A6000. Both are amazing machines. The A6000 starts to shine. It has 48 gigs of VRAM over 1 billion records. So that's something internally we're working on, is how to push the A6000 to this new level. And a shout out to Lunar G for all the cutting edge work they did on the benchmarking in this area. So when we look at people love the topic of orchestration. How do you, all these nodes and these network clusters, all these things, how is that all happening? Well, if you look at orchestration, it has an overhead. And you can see that here. So when we move from 0 to 1 billion records, the cost of orchestration is increasing. Your efficiency decreases. But the GPU is pretty much the best orchestrator. It is absolutely the smartest, most cutting edge thing. And you can see the penalty of orchestration is quite slight. When you move between 500 million and 1 billion records, the penalty is pretty low. Okay, now let's pull back and look at this kind of compute data work. Again, CPU versus GPU. Same thing, a lot of programs, common things like these are low scales, right? Compared to 1 billion records, we're looking at 900K, we're looking at 10 million, but it carries across. The GPU wins across all categories. And then so you can see that when you start off low, you start off at 900K, they can have some sort of stay in the range a little bit, but as soon as you start picking up or doing anything complicated, the GPU just shines. Okay, now let's look at the IDE. So here's an interesting area where is that it's a new idea to have display data science, data software display on the GPU. And if you do that, you get this this kind of thing where you can visualize better, you can move at faster speeds, you can see the impact of decisions. This data loop is collapsed. This concept of big data WYSIWYG. And Python notebooks have kind of swept data science as something popular, but you can see we're all familiar with this. If you have a pandas data frame, you can't see all your data. It's cut off. In the past, I used to go to files, or I'd have a whole bunch of workarounds that I'd use. You can sort of jerry-rig your own system together for this, but having everything right there on the GPU has power to it. And we'll show that in a second. So this brings into the idea of the spreadsheet on the GPU, that you can have this flexibility, this decision loop, like why does the work of the coder, someone in Python, and the spreadsheet need to be separated? Couldn't those be brought together? And then they can click on this and then go through and look at their data. And I always found that a problem. It's like this visual inspection pass, this kind of, oh, is that okay? Is there something wrong here? Just seeing what you're doing has a lot of value. Okay, so next we're going to look at a quick example of a GPU-driven environment. This is row 64. We just loaded up 30 million records. You can see we could run some filtering, and just the speeds that things are happening, the load speed for 30 million records, the scroll speed, just the power of the GPU expressed in an interface and compute operations, like doing a sort here. You can see that we're going to sort very quickly. It's under 2 seconds. And things like filtering, these are all available and fast. And this is where you really see the power of the GPU. Okay, now let's get into geography. Geography is an interesting area because real-time ray tracing was the breakthrough of 2021. Personally, I think the industrial scale, the breakthrough with real-time ray tracing happened in 2020 with the release of the Ampere architecture. And you can see here we're timing. A side note, we know that Blender has GPU ray tracing. We're just doing a comparison of CPU versus GPU here. And same thing happening with data work. It crushes it. The GPU is orders of magnitude faster. In fact, this is a bit high. We can hit, we're testing on the A6000 lately, and we can hit frames of up to 100 frames per second on a large geography scene with 8 rays and 16 bounces happening. So this is a new thing. This is a new way of seeing detail to have finished work happen in real time. So when you first start looking at geoanalysis with ray tracing, the first thing is it's pretty cool. You can get a lot of different looks. The visual range that you have accessible is really good, and that you can move closer to a finished look or a more final look. It's also very good for doing mapping in a way that's ready for presentations and communication. It can be more diagrammatic than something like Google Maps or traditional mapping software. We're looking at, we've got some just a small amount of data looked up here tracking things in terms of coordinates. You can drive materials, and just this whole world of data and geography and communication, building a communication layer with your geoanalysis. Here's showing some rendering features like caustics, translucency, HDRI rendering. All these things are just incredible tools with ray tracing. Okay, so looking forward, there's these new areas. There's a graph evaluation, there's a compiler, there's the potential to be linking machine learning with a GPU-driven data environment. These are areas we're doing a lot of research. We know a number of other teams doing exciting research in these areas. And so they're just something to keep your eye on as the GPU frontier expands. So big picture, what have we discovered? What is the learning of all this research? Well, at its core, I think if you're immersed in a real-time environment, you can make better decisions, you can make better discoveries. At the moment, the GPU is the kind of flagship performance hardware that is just taken off 100 miles an hour. It has the potential to break down silos. You have WYSIWYG big data. Big data, instead of being a thing that you go wait a week or a day or overnight for, you see. And the ability to communicate with this new level of visual quality of ray tracing. We'd like to thank NVIDIA for the opportunity to present here and for helping us with their Inception program. We're very grateful. We'd like to thank our audience and all our partners, Imaginary Spaces. We'd like to thank Lunar G. We'd like to thank everyone who's helped us. Thanks for attending the talk. I would recommend an additional talk. We are big, we really like Kim Library, and he's doing a talk on in-camera VFX and virtual production. I remember 12 years ago, I was talking with Kim Library, and he was doing taking a lot of big risks, thinking about the future of the GPU. And at the time, I couldn't, I was like, I don't know. I just couldn't process it. And so he's really been a trailblazer in this industry. He's on a seminar Wednesday the 14th at 10 a.m. PST. So thank you very much.